Howdy class. So today we are actually skipping to chapter 12 for a little bit before we go back to chapter 10 because this stuff probably should just be in chapter 10 anyway. But there will be some things in here that might not make complete sense because it is a later chapter, but I will try to explain them as best I can, or at least as well as you need them to be explained for our purposes. So we're talking about phase changes. There are, as you probably know, three phases of water, or at least three phases that we care about realistically in the practical world. There are three phases of water: solid, liquid, and gas. And these three phases have different properties, as you know. So there are solid water is has a lighter smaller density actually than liquid water. That's why ice cubes float. There's a lot of other things, obviously, that are involved in those different properties. And because these phases have different properties, they need to be separated from each other, and they are separated by something called phase boundaries. So phase boundaries aren't, physical boundaries, but they are energy boundaries. So we need certain amounts of energy to go from one phase to another. When a substance goes from one phase to another, we call it a phase change. And phase changes, like I said, require the absorption of or release of energy. So to get over that phase boundary, we need to add energy or we need energy to be released. So these are the, five different examples of the phase changes in water, or carbon dioxide. That last one's carbon dioxide. And I should have said that there are these three phases of, everything, every substance, not just water. So we're talking about phase changes for all substances, not just water. But these phase changes are freezing versus melting. So freezing and melting are two that go together, going from liquid to solid or solid to liquid. Evaporation or vaporization, along with condensation, going from liquid to gas or gas to liquid. And then sublimation of dry ice is going from solid carbon dioxide to gaseous carbon dioxide. And consequently, there is also the opposite process where we go from gas to solid, which is called deposition. So these are phase changes. You are familiar with all of these, but you may or may not know that they require the absorption or the release of energy in addition to just the temperature required to make the change. So we're going to get into that now. So this is a, figure of all of these different phase changes. So when we have increasing temperature, we go from solid to liquid. So we melt or fuse our solid into the liquid form, and say that would be solid is down here, liquid is here, and then if we keep heating it up, we will vaporize our liquid and we will go from liquid to gas. So up here is our gas state. And if we skip past the liquid state, we don't stop here. We go straight through. That's called sublimation, where we go from solid to gas. You can see the different properties of our solids, liquids, and gases here. And they spread apart due to increasing temperature, increasing energy, which allows the molecules to get further away from each other, essentially, as we'll see in a little more detail here. And then these are the opposite, or the reverse of those processes. So deposition is gas to solid, condensation is gas to liquid, and freezing is liquid to solid. So this is our liquid state, goes right through that liquid label, and this is our gaseous state, and this is our solid state. All right, cool. So, like I said, simply heating a substance to its boiling point, or at least what I hinted at, simply heating a substance to its boiling point is actually not enough to cause full vaporization of the substance. So if you just heat your water up to 100 degrees Celsius, that won't actually be enough for all of the water to boil, for all of it to vaporize. You need additional energy. Additional energy is required to cause the molecules to transform from the liquid state to the gas state. And that energy is called the molar heat of vaporization, or delta H vaporization. So heat versus enthalpy, if you remember, these are the same thing. Q and H are equal to each other for constant pressure processes, which is pretty much everything that we're going to talk about. So we sometimes say molar heat of vaporization, sometimes say molar enthalpy of vaporization. We mean the same thing. We mean this delta H of vaporization. This is the heat required to vaporize 1 mole of a substance. So it's molar, we're vaporizing 1 mole. So we need more heat. We require more heat to vaporize more than 1 mole of a substance, or a fraction of the heat required to vaporize a fraction of a mole of a substance. So it's all based on this 1 mole thing. So that is a conversion factor, actually. So delta H vaporization is a conversion factor between heat, energy, and moles. So when we have a certain number of moles, we can find out the heat required to vaporize that certain number of moles using this as a conversion factor. And delta H of vaporization is related to a substance's intermolecular forces. So we're going from the liquid state, or phase, sorry, to the gas state, or phase. We kind of use those interchangeably here. So we're going from liquid to gas. So we have molecules that are pretty close together in the liquid state. We got a, decent density there for liquids. And then we're going to a gas state where all the molecules spread apart. We need more energy to spread apart those molecules when they are held together more tightly by strong intermolecular forces. So the higher the intermolecular forces of a substance, the more energy is required to vaporize that substance. So delta H of vaporization is higher. We actually learned this a little bit, more or less, without using this term in way back when we started talking about intermolecular forces in chapter 7. So we just talked about the intermolecular forces of, say, benzene and compared it to its boiling points. We had a couple tables like that. Stronger intermolecular forces equals higher boiling points, but that's actually the same for delta H of vaporization. So higher or stronger intermolecular forces equals higher boiling points, which in turn equals higher delta H vaporization. So these are all related to each other. The stronger the intermolecular forces, the higher the boiling point, and the higher the delta H of vaporization. The more energy is required to vaporize those molecules and spread them apart. Okay, gonna erase a little bit here. So it's a little clearer what I'm trying to emphasize. So this is a little refresher on intermolecular forces. Water's going to have the strongest intermolecular forces of these 4 because it has hydrogen bonding. So it has the highest boiling point of these 4 and the highest delta H of vaporization of these 4. Let's see what's next. So after water, we've got either diethyl ether or benzene coming in next. And this one's a little tricky. This one you might not expect. Diethyl ether has this oxygen in the middle, which means it should be, it may or may not be polar, depending on how we draw it. So let's see. If we draw, so we've got carbon and another carbon over here. There's 3 hydrogens off of that one, 2 here, and then our oxygen. And we got another one over here, doop doop, and carbon, 3 hydrogens. So this one might actually be So this one is a little polar just because of the structure. So I didn't draw, this is kind of a Lewis structure. If I drew it more accurately, we'd have oxygen, and these carbons would be making a bent shape with the oxygen. And we'd have another carbon here with hydrogens on it, carbon here with hydrogens on it. I'm not going to draw the hydrogens in, but we'd actually have a shape kind of like this, because oxygen would have two lone pairs, so it would actually be a bent structure. So yes, this would be polar. So if it's polar, that means it has dipole-dipole bonding. So you might think that it has a higher boiling point and delta H of vaporization than benzene, which is just a hydrocarbon. I'm going to erase this so you can see everything again. So benzene is just a hydrocarbon, but benzene is a special organic molecule. As we've talked about several times, it's got this structure with double bonds, which actually means that we can separate our electrons all the way around. Those electrons are delocalized, so they are not focused on any one point of the benzene ring, but they are delocalized over the whole thing, which really helps with its polarizability, as your textbook explains. So benzene actually has a higher boiling point and delta H of vaporization compared to diethyl ether, even though diethyl ether is polar and benzene is not. So polarizability, again, can come into play a lot here. But we're not actually talking about intermolecular forces, right? So the main point is that these are correlated. Boiling point, when boiling point is higher, delta H of vaporization is higher. When boiling point is lower, like with methane, really, really low, delta H of vaporization is pretty low. So methane here is the smallest one. It's got only dispersion forces, and it's really tiny, so those dispersion forces are not very strong. So the boiling point, super low. Delta H of vaporization, super low. So there was your review of intermolecular forces for, you know, the rest of the semester pretty much. So let's keep going. The reverse process of vaporization is called condensation, as you probably know. And condensation can be caused by cooling a gas and or increasing the pressure of the gas. So we could have both, or one or the other. Both can cause condensation, cooling it to a low temperature or increasing the pressure to a really high pressure. Both of those cause the gas molecules to come back together and condense into the liquid form. Why are we talking about this? Because we're going to be talking about phase boundaries and phase changes and phase diagrams in our next set of lectures. So we want to talk about some of the points on those phase diagrams. And one of them is called the critical temperature of a substance. So TC is the critical temperature of a substance, which means that at temperatures above TC, the substance cannot be condensed. It cannot be liquefied. The substance has to stay a gas at temperatures greater than the critical temperature. When temperature equals the critical temperature, though, when we are right at the critical temperature, the pressure required to condense the substance is called the critical pressure. So when we're at the critical temperature, we're probably still going to be in the gas form unless we apply this critical pressure, which will be enough to condense the substance even though it's at that really high temperature. Anyway, those will come up again when we look at our phase boundaries and phase diagrams, but another, like, you know, what's the word, vocab word for you for this set of lectures is supercritical fluids. Substances at temperatures and pressures above critical temperature, critical pressure are called supercritical fluids. So we're above both the critical temperature and the critical pressure. So we're way above. These are called supercritical fluids. And these have interesting properties because, well, we're above TC, so we're kind of We should be a gas, right? Because at temperatures above Tc, the substance cannot condense, but we're also above the critical pressure, which is causing those molecules to want to be closer together. So these are supercritical fluids because they are really unstable at these super high temperatures and super high pressures. But that's enough of that for now. So let's talk about a different phase change. When a substance undergoes a phase change from solid to liquid, this is called melting, as you know, but sometimes also called fusion. We're fusing those solid molecules together into a liquid. We are kind of molding them closer together, but also in a less organized fashion. So that's why we call it fusion, because we're getting kind of less organized, but still close together. So melting or fusion is going from solid to liquid. The reverse process is freezing when we go from liquid to solid. The melting point and the freezing point, as you probably know, are the same temperature. So the melting point of water is 0 degrees Celsius or 32 degrees Fahrenheit. That's when the snow will start to melt. That is our melting point, but it's also the freezing point. So that is, if you cool it down to that temperature, your liquid will turn into a solid. So it just depends on if you're heating or cooling your substance as to which term you use, whether you're melting or freezing. And we have a special term for when we're at 1 atmosphere of pressure, and that's called the normal melting or freezing point. So this normal term comes in when we're at 1 atmosphere of pressure, which is, actually the melting or freezing point that you're familiar with, because 1 atmosphere of pressure is approximately what we have at sea level, which is where we normally operate. And then at this melting or freezing point, it's one other important thing to note is that the substance is in a state of dynamic equilibrium. So this actually also happens at the boiling point. We have a dynamic equilibrium between liquid and gas, but now at the melting or freezing point, the substance is in a state of dynamic equilibrium where both phases coexist. So at this melting or freezing point, we have both liquid and solid water in the same system. So when you get to that point, you're going to have some pieces of ice and some really, really cold water coexisting. So that is what we call dynamic equilibrium, where some of that ice starts to melt, but then it's still really cold, so it could start to freeze again, and we go back and forth between the two, where we have both phases coexisting at the same time for, different parts of the system, different molecules. When a liquid is rapidly cooled below its freezing point, we call this supercooling. Supercooled liquids are really unstable, and sometimes we do this to perform a process called recrystallization, which is used for purifying different substances. We heat it up so that we can, boil off some of the impurities, and then we cool it back down really fast. We supercool the substance so that we can, recrystallize by adding seed crystals or scratching the sides of the container, which helps the solid start to form at this temperature. And then the solid that forms will be more pure than what we started with, because some of the solid will, or some of the substance will not recrystallize, and that's the less pure parts. The crystallization will happen at that temperature for the pure substance. So we right around that temperature of supercooling, we can separate the solid and liquid and get a more pure solid substance. And you'll learn more about that in organic if you keep going in chemistry. So once again, very similar to what we had with vaporization, heating a substance is not enough to cause full liquefaction of the substance at its melting point. We need additional energy to cause the molecules to transform from solid to liquid. And this additional energy is the molar heat or molar enthalpy of fusion, the heat required to melt 1 mole of a substance. So molar heat melts 1 mole of the substance. And just like delta H vaporization, delta H fusion is also related to the substance's intermolecular forces. And that means that the melting point and delta H of fusion are also related, just like the boiling point and delta H of vaporization were related. So water has a pretty low, well, water has a pretty high melting point compared to the rest of these substances actually. And it's got a decent delta H of fusion. The melting point of argon is really low. Delta H of fusion is pretty small. But then we get some weird ones in here where the melting point is a lot lower than the melting point of water, but the delta H of fusion is actually higher. Same here. So these substances are a little weird. These substances have really low melting points, but they still have fairly high delta H fusion, and that's because going from solid to liquid is a bit different than going from liquid to gas. So solid to liquid, they're still pretty close together. So we don't need as much energy to separate them as we did with delta H of vaporization. So it's a little less correlated with intermolecular forces, and you can look at your book and see how they describe this process. But it's a little less related to intermolecular forces because solid to liquid is a less dramatic transition, I would say, than liquid to gas. And then we also have some substances that have unusually high vapor pressures, and they skip over the liquid phase entirely. These undergo sublimation during heating and deposition during cooling. So sublimation is when we go from solid to gas. Deposition is when we go from gas to solid. And the energy required to sublime 1 mole of a substance is its molar heat of sublimation. So same kind of concept as we had with oops, that should be sublimation. Sorry. So same kind of thing that we had with delta H fusion and delta H vaporization. Delta H of sublimation is the energy required to sublime 1 mole of a substance. And you're going to soon learn something called Hess's law in chapter 10. When we jump back to chapter 10, you're going to learn Hess's law, which will explain this here equation for you in more detail. But basically, this might be kind of self-explanatory. You might understand it already because it's pretty straightforward. The delta H of sublimation is equal to delta H of fusion plus delta H of vaporization. And that's because we're going from we're going from solid to liquid to gas. Oops. With, this is delta H fusion, and this is delta H, oops, vaporization. And when we go from solid to gas, this is just, skipping over the liquid portion. So delta H of sublimation is the sum of those two things because we're going from one state to another. So delta H enthalpy, as we have learned, is a state function. So going from the initial state to the final state, the delta H is actually just going to be the sum of those two delta H's. And we're going to learn more about that with Hess's law in chapter 10.